So well, actually, before I do this, so first we're going to talk about in section 2.1. We're going to talk about piecewise functions. And usually when you start learning about piecewise functions, the easiest one to consider at first is the absolute value function. Now, all of you are pretty good at computing absolute value. If I ask you, for example, to compute absolute value of 3, you should be able to do that. What is it? 3. And if I ask you to compute absolute value of -2, you'll say 2. How do you do that? So I didn't do that before. I did that. So I'm repeating myself right now. So did I remember me doing something like this? Did I do something like that? All right. Well, why was I talking about absolute value then? Well, okay. Well, if you're all nice and happy, how would you compute something like this? Absolute value, I know I didn't do that example. Absolute value of 1 minus square root of 2. What is the absolute value of 1 minus square root of 2? I'll put two numbers up. Absolute value of 1 minus square root of 2, and absolute value of 3 minus square root of 2. So you're okay with just, 3, absolute value of 3 is 3, absolute value of -2 is 2. But how do you do absolute value of these crazy looking numbers? So let's go back to the simple example. Why is absolute value of 3 equals 3? You know the answer to that. Don't get scared by the square roots. Tell me, why is the absolute value of 3 equals 3? This is distance away from 0, but that's not how you computed it, right? When I ask you, what is the absolute value of 3, you weren't thinking about the number line where the 3 is and then measuring the distance. By the way, you're absolutely right. That's what absolute value of 3 means. But how did you compute that? Just be honest with me. How did you go? Absolute value of 3 equals 3, which is correct. How did you get that answer so fast? Well, yeah, you looked at 3. 3 is a positive number, so it's 3. How did you get absolute value of -2 so fast? So you looked at -2, you realized that it's negative, you made it positive, right? How do you make a negative number positive? Think about an algebraic or arithmetic operation, because there's no such operation as erase the negative sign. Somehow what? You're right. So this is what you did. You took -2 and you multiplied by -1, right? That's really what's happening. So apply the same skill here. Look at 1 minus square root of 2. The number itself, 1 minus square root of 2, is that a positive number or a negative number? What do you think? Why? Yeah. Well, square root of 2 is more than 1. So 1 minus more than 1 is less than 1, right? So how do you make a negative number positive? So it's -1 times 1 minus square root of 2, right? So in other words, it's a square root of 2 minus 1. It just basically gets flipped. Square root of 2 becomes positive, and 1 becomes negative, right? If you distribute -1, Well, then how about absolute value of 3 minus square root of 2? Is 3 minus square root of 2 a positive number or a negative number? Why? Well, what did he say then? Yeah, but what's the square root of 2? Can you guesstimate it? Basically, square root of 2, yeah, square root of 2 is less than 3, so 3 minus less than 3 is positive or negative. And how do you take absolute value of a positive number? You just don't mess with it, right? So then it's just whatever that was, right? Since the number itself is greater than 0, then we'll mess with that. This number is less than 0 multiplied by negative 1, right? So this is what a piecewise function is, because we had to analyze what is the input of our function. Is it positive or negative? And that actually gave us two different computations. So really, the absolute value of x function is defined like this. It's negative x if x is less than 0, and it's x if x is greater than or equal to 0. So I didn't put this on the board before. All right. My mind is playing tricks on me, because I did that in another class, in 055, not in algebra. Wow, 055 is ahead of you. That's crazy. I'm being nice to you. Okay, so the way this notation works, this right-hand side acts like a filter. When I ask you, what is the absolute value of negative 6, let's say you don't understand what absolute value is. You don't understand the symbol. But you understand this definition on the right. The way you read this, all right, so here's a function. The value of the variable is negative 6. So x equals negative 6. Which one of these inequalities does negative 6 satisfy? Is negative 6 less than 0, or is negative 6 greater than 0? Less than 0. So this is the inequality that negative 6 satisfies, right? So therefore, this is the function that negative 6 is going to be plugged into. So that becomes negative of whatever the x was. X was negative 6, so that's positive 6, right? The absolute value of negative 6 is positive 6. Really an overkill. You will never compute absolute values like that unless it's crazy ones. But it's just kind of an introduction to how that notation works, right? So this right-hand side acts like a filter. It tells you, depending on the value of x, what is the function that you're playing with. Does that make sense? So that's why we call it a piecewise function. It's defined differently depending where x falls in. Okay? I can graph this function. Most of you know the graph of the absolute value function. What is the graph of the absolute value function? Does anybody remember from earlier math? Yeah, it's a v. But let's say we don't know that. All we see is this little definition. All it says, the function is x if x is greater than 0. Well, what is the graph of x? It's a line. The y-intercept is 0. The slope is 1, right? So it's that, right? That's y equals x. But starting at 0, because it's only true for greater than 0 on the x-axis, right? So here, all the x's that are greater than 0, the value of the function y equals x. Well, all x's that are less than 0, the function is negative x. Well, what is the graph of negative x? It has a negative slope. So it's actually coming down to the origin, right? This is y equals negative x. So yeah, it is gives you the V shape. But it's two pieces. Every time you see graphs that have those sharp corners or that are disconnected, most likely that's a piecewise function, okay? Because it's kind of came up in pieces. Is that okay? All right. So let me give you this example. So here's a piecewise function f of x equals 2x plus 1 if x is less than negative 2, and then it's 3 if x is between -2 and 1 like that. X is greater than or equal to -2 and less than 1, and -2x plus 5 if x is greater than or equal to 1. So this function is defined in 3 pieces. Okay? So on the exams or in your homework, you'll get questions like that. Here is a function. Can you evaluate some of the values? Like, can I ask you, what is f of 2? So f of 2 means x equals 2, right? And then you have to decide which one of those 3 filters x equals 2 satisfies. So you have x less than -2, x between -2 and 1, and x greater than 1. Where does x equals 2 falls into? The last one, right? Do you see how that works? So then this is the function. That's where it's going to get plugged in. So that equals -2 times 2 plus 5. We're plugging the value into the very last function, because that's where 2 is. So that's -4 plus 5. So that equals 1. Is that okay? Does that make sense? Common mistake that I see a lot is that a student will plug 2 in all 3 places and will give me 3 different answers. Now, what is the problem with that? Is 1, that's no longer a function. You cannot plug in 1 value and get 3 different values as an output. Functions don't do that. So that tells me that a student does not understand the concept of a function, and then, well, then you're just plainly wrong about how this whole notation works. Does that make sense? One of you will make that mistake on a test. I can make a bet right now. Who wants to make a bet? $100. Leaving the problem blank. This class. Leaving the question blank counts as a mistake, by the way, because I've seen you guys trying to trick me like that. Oh, just don't answer that at all, then nobody made that mistake, and we'll win the bet. Answering the question, I'm not, leaving the question blank means, boom, that's wrong. You want to make the bet? All right. Probably the ones that are not here right now. Okay. Well, good. So at least that probably will remind you when you face that question. Just plug it once. What if I ask you f of 0? How do we do f of 0? Three. That's right. F of 0, x equals 0, satisfies the middle inequality. While in the middle, the function is a constant. It's always 3, regardless of what x is. So the answer is 3. Right? Because that's the function. It's just 3. If I ask you what is f of pi over 4? That's a fun question. Yeah, because pi over 4, pi is 3 point blah, 4 is 4. So it's definitely less than 1. So it still falls into this category. So it's still 3. Is that okay? F of -7. Very good. -7 satisfies the top inequality, so that becomes 2 times -7 plus 1, so -13. How about f of -2? 3. -2, that's where it satisfies the middle one, because that's where it equals to. By the way, you will hardly ever see any overlaps in this inequality. See how -2 only satisfies the middle one. Because if it satisfies 2 inequalities, no longer a function, unless the 2 pieces meet. Okay? I can ask you to graph this thing. And that's always fun. Again, a very common mistake is just to graph 3 lines and just have 3 lines on the same graph. The problem with that, it will definitely fail the vertical line test, and it's no longer a function, right? You would know that? But you should definitely start with just graphing all 3 lines. Just graph all 3 lines, see what it looks like. Here's the first line. The y-intercept is 1, right? The slope is negative 2. So that means what? Down 2 over 1. So here's the first line, right? Oh, yeah, slope is positive 2, then never mind. Slope is positive 2, up 2 over 1. So here's that line. Yes. The other line is y equals 3. So that is bad, right? And the other line is 5 on the y-axis, and then negative slope, so down 2 over 1, so something like that. Oh, that's a big mess, right? Well, one thing that we can do now is to erase parts that we don't need. And what I mean by that, so this first line, 2x plus 1, really works for x is less than negative 2. So whatever negative 2 is, this line should not pass this little threshold, right? This is the only chunk that we need. This chunk right here is the only piece that is for, the 2x plus 1 less than negative 2, right? So I'm going to erase the rest of that line. I don't need it anymore. I'll still keep that all connected. And I'm going to leave this as an open circle because it's strictly less than negative 2. Okay? You see what I did? I just look everything less than negative 2 is that line. That also means I don't need this part of the constant line, and I don't need this part of that straight line, but that's a different story. The constant will start with a filled-in circle because it's greater than or equal to, and it will go all the way to positive 1, right? Oh, I need to switch I'm still on the magic pen. And it will go to positive 1 somewhere in here. So I don't need anything before that here. I don't need anything past there. Right? And these two lines actually meet. They actually meet in that corner. Right? Because when x equals 2, these two lines at the same height. So this is the graph of that function. 3 pieces. This is a weird way of doing that. It's just graphing all 3, then erasing parts that you don't need. Or you can just graph the parts that you need. That's a little harder. We can do it that way too. And I'll show you how to do it that way. But did that make a little sense? How you graph all of them, then you erase what you don't need.
Third circle you just drew, shouldn't that be open?
Yes. Because it's open. Here's the thing. If I ignore this line, it's open over here, right? But where does this line start? I mean, if I plug 1 into that line, I'll get what? 3. So actually, this line starts at that point, and this third line fills that point in. The 3 has a hole, but then that other line comes into that hole. So they actually connect in that spot. What? Not really, just... Another way of doing this. Let me take this, well, because okay. Another way of graphing this function is to do this directly, actually graph pieces that you need. Because again, remember, in order to graph a line, all you need is a point and a slope. Right? So think about this first line, 2x plus 1. So it only kicks in before negative 2. So it's a line of a positive slope that stops at this threshold. Do you agree with that? It's going to go all the way here on the left, and then it's going to stop here. So the question is, well, how high is this line at x equals -2. If you plug in -2 into that line, what do you get? It's -4 plus 1, so it's -3. So it's actually, it starts at -3, but we're going to make a hole in it because, technically -2 is not part of it. And then the slope is 2, meaning, it's like that. The slope is over 1 up 2. So here's that line. Right? You can do the slope backwards. You can, down to over 1, the same as up to over 1. Okay. Then in the middle, it's +3, and it goes from -2 all the way to +1. Right? This constant one, it's a constant between -2 and +1. And then the third line, just take 1, plug it in here. What do you get? Because you need a point. So you get 3. So it actually comes in, fills that circle. And from that point, the slope is -2. So you go down to over 1. So you do that. Right? And you still get the same graph. Any questions on this? Let's try another one. What if I define a function x plus 1 if x is less than -1, 2x plus 2 if x is between -1 and +1, and then -x plus 1 if x is greater than 1. I just want to graph this. And I'm going to do this directly without graphing all lines and erasing things. So we have 2 thresholds, one at -1, one at +1. So this is where the values of the function are going to change. So the function itself is going to change. So let's try this first one, x plus 1. So if I plug -1 in for x, what do I get? 0. So this function comes up all the way to this point, right? It gets really close to that point because it's not quite on that graph. And the slope of that line is 1. So I need to make a line of the slope 1 that's leading up to that point. So this will be x plus 1 for x is less than 1. It just comes up and it stops right there. Is that okay? Then in the middle, it is 2x plus 2. So you can do 2x plus 2 in the middle. Y-intercept is whatever. And then it's up 2 over 1. So actually, it fills in this dot, right? Does it appear that they have different slopes? That was my intention. One has a slope 1, that one has slope 2. So it should probably be more like this. The other one is sharper. And then finally, it's -x plus 1 from 1 and on. So if I plug 1 in here, I still get 0. So here's a little open circle. And then slope is -1, down 1 over 1. So there we go. So this is the graph. You have slope 1, then it jumps slope 2, and then it drops down and goes that way. What do you think of that? Let's try this fun function. 5 if x is less than 1, and x squared minus 25 over x minus 5 if x is greater than or equal to 1. What is the domain of this function, first of all? Well, everything but 5. Yeah. So x cannot equal 5, right? We can see that from the denominator. Everything, everywhere else it seems to be okay. So we have to keep that in mind. X cannot equal 5. Now, we can simplify this portion. Do you agree with that? It is x minus 5, x plus 5 over x minus 5. The numerator factors. So x minus 5's cancel, so that becomes just x plus 5, but then keep in mind that x cannot equal to 5. Right? But I can still sketch the graph of this function. It's going to look something like that. So the function changes at 1. So for everything less than 1, the function is just a constant, y equals 5. So the graph is just a flat line leading all the way up to here, and then an open circle. Right? So this is y equals 5 for everything less than 1. And then when x equals 1, if I actually plug that value into my second function, what do I get? 6, right? It jumps 1 unit up, and then it has a slope of 1, so it goes 1 over 1 up. The only problem is that somewhere at x equals 5, there is a hole in the graph of this function, because it's undefined when x equals 5. So that's showing that x cannot equal 5, so there's a little hole in it. Isn't that an interesting graph? Yeah, sure. Are we good? Okay. So in this section, especially since, you've read it and I have proof, there were questions like, find the maximum, find the minimum, find the intervals where the function is increasing, find the intervals where the function is decreasing. And it's all based on what the graph of the function looks like. Okay? So that means we have to start graphing our functions, and most likely using graphing calculators or whatever, which we mostly probably don't have, which is okay. So the website that we've been using in this class rather successfully for graphing is the fooPlots, and I probably showed it to you on day 1 or something like that. So fooPlots.com. Is the regular internet failing us now? We have some technical issues this semester. It's an awesome website. I know. This is not just, let's try again. Well, this is just beautiful. All right. I guess fooplot is down. So there's a lot of that too. What is Desmo? Here we go. So we can use that. Doesn't matter. They're all the same. So, I can type in any function I can think of. And let me see, just to double check how their notation works. So yeah, see x squared plus 3x minus 5. So yeah, so you see, oh, this is nice. It graphs our function as we go. What if we do a fraction? What if we try that x squared minus 25 over, x minus 5. Now you see it's not as smart as we are. It should have put a hole in there, but it didn't. Oh well. But it gives us a good idea of what the graphs look like. So we'll be using things like that. So you don't need a graphing calculator. If you have a graphing calculator, good. If you don't have a graphing calculator, but you have a PC type of computing machine, it has that Microsoft Mathematics add-on that's a graphing calculator and more, and it's free. You should install it on your PC if you have one. If you're running those bit and Apple thingies, then you probably don't have that. Well, then install that if that works. Okay, it's that, then you're all set. So let's do a word problem. So let's do a word problem. I want us to do question 42. Oh, actually. Oh, question 42 was kind to us. It gave us the graph. So we don't need a graphing calculator for that. Okay, you want to read the story? So does the story make sense? Now think about this. So we're building a fence here. We're building a fence here. We're building a fence there. And we're building a fence there. But we're not going to build next to the river. So the picture looks something like this. X, X, X. And let's call this Y. Okay? And there's a river over here. So the first question is asking us to express the total area of both, of this whole thing in terms of X. So the way we think about this problem is that we really have a rectangle that is, this side is X and that side is Y. So what is the area of a rectangle then? This is X and that's Y. What's the area? X times Y. Have we fulfilled the assignment? No, because we want to do it in terms of X. This has two variables. So how do we express? So basically at this point we need to express Y in terms of X. Well, how can we do that? Right? Because that's where we're at. So how do we do that? What do we know about the total fencing used there? 360, right? So if I add x plus x plus x plus y, so 3x plus y, that should equal to 360, right? So from there we can say that y equals 360 minus 3x, and we can take this expression and substitute in there. Okay? So then the function becomes, area as a function of x is x times 360 minus 3x. You can distribute that, whatever, if you do that, we'll end up with 360x minus 3x squared. Does that make sense how we did that part? Now part B is actually going to be very tricky. If I just give you that function without the cow story, just, 360x minus 3x squared, what is the domain of that function? All real numbers. But now we have to think about domain of this function in the context of this problem. Because now x cannot be negative, right? Negative x does not make sense. Do you agree with that? If x equals 0, I mean, can x equal 0? I mean, technically, we can get very close to 0. We're just not building a fence. We're just building fence next to the river, right? We're just fencing off the river, like 360 yards of fencing, right? But theoretically, all right, so it's a stupid idea, but we can do that at least. So the domain here is from 0, but what is the largest value x can be? Well, the total fencing is 360. I still have to build three x's, right? So I mean, the worst case scenario, I'm going to build 3 fences that are touching each other without y, right? That's kind of silly, but I can do that. So what is the length of each fence then? 120. So this will be the domain of this function between 0 and 120. And actually, when you graph it, this is the graph, right? It goes from 0 to 120. Now, whether you include whether you include those endpoints, that's almost irrelevant. But even without the graph, if most of the time you're not going to be seeing the graph of this function. Later we will learn how to graph this function fast, but we can use your graphing calculators or whatever. So what is it? It's 360x minus, what's wrong with that? Oh, maybe I should tell them it's times x. (360) times x minus 3x squared. Okay. Oh yeah, this is going to be a fun-looking graph. Okay, so this is the problem you will encounter with your graphing calculators. This is where you have to change the settings. Where are my settings? The window. Does this thing have a window? I mean, this graph is going to go really, really up high. Yeah. This is the point that we want. See, this is the, graph settings. Okay, here we go. Let's x-axis to be from 0 to 120. Here we go, that's perfect. Okay, so you will see this on your graphing calculators. When you get graphs that are weird, you don't see graphs, because maybe graph happens, all the way outside your viewing window. So in your graphing calculator, you have this window button that you go in, and you can start changing the bounds. All those online graphing pieces of software have that too. You just have to find it. This is the first time I'm using this one since fooplot seems to be down, but anyways. So the question was, the last question on this problem, just using the graph, find the dimensions that will give us the maximum area. So just by, what do you think the maximum area is located on this graph? Without even, I know this is funny, without reading the book even. Where is the maximum? The top, right? This is the maximum. So x has to be 60. What is y? Can you tell me what the y is if x equals 60? Yeah, so it's 360 minus 3 times x. So that's 180. So how's that? Yeah?
What is the y value of the graph?
Oh, well, that's actual area, okay? Because remember, this is our function is a of x, so a is the area. So this is really the x, whatever the x is, and this is the total area. So the largest area that you can achieve would be 10,800 square feet or yards, whatever the unit. So yards. So that would be the largest. The actual maximum area is, yeah, if you use 60, 60, 60 and 180 across, will give you the largest area of 10,800 square yards. Let's do another one. Let's build a box. I should be able to read this. It's a little messy now. Can you read this? So, you have yourself a square piece of cardboard, you cut out the corners, you fold, you got yourself a box. Okay? Now, what is the volume in general, the volume of a rectangular box? How do you find the volume of a rectangular box? What do you do? Length times width times height, right? So length times width times height. So here's that box. So the height is easy. The height is x, right? This is the height, because that's how you folded that. So the height equals x. What about the length and width? They're going to be the same since we started with the square. But what will be the length of each side, provided that the original piece of cardboard was 12 by 12? Right. So that will be 12 minus 2x. Because you started with 12, right? This is 12. From here to here, it's 12. But then you're cutting out 1x, and then you're cutting out the other x. So it's 12 minus 2x. Is that okay? So this 12 minus 2x by 12 minus 2x. So this is 12 minus 2x squared. So here's our volume as a function of x. Okay? So that's A. Now, what about the domain? Again, if I just give you this function without the story about the box, you're going to say the domain is all real numbers, there are no problems. But here, again, we have to be tricky. What is the smallest value x can be, theoretically? Yeah, I mean, so you're not building a box, you're just staring at the piece of cardboard, right? So 0. And we can do it like that. What is the largest value x can be? The whole thing is 12. You're cutting from both ends. Well, then 12 you're going to overcut. So 6, right? Because then you're going to meet somewhere in the middle. So meaning you just cut your box into 4 squares, and then you're like, oh, that didn't work. So you're not going to get yourself a buck. So up to 12. So it'll be the domain. So this kind of helps to pick your calculator viewing window, because now we have to use the calculator to graph it. So again, I can just type in this function as it appears into my newly discovered graphing tool. So what is my function? It's 12. 12 minus 2x squared times x, right? Now, you see, I didn't change my viewing window from the previous one, so I should do that. So just from 0 to, well, let's go from 0 to 7. Now, you see what's going on with my height? Because the height remained from the previous one. So what should I change it to? Maybe from 0 to something more humane. How about 100? Okay, maybe not enough. 150. Here we go. Okay, this is our graph. So that's from 0 to 6. Then it starts doing something else, but we don't care when it does after 6, right? From 0 to 6, that's the point we're after. So this is actually nice. It tells you what the point is. So what does x have to be in order to achieve the maximum value in that box? 2. What would that maximum value going to be? What actual volume when it's at the maximum? 128. Yeah. So based on this picture, we will say that the maximum is at x equals 2, and the maximum volume is 128 cubic centimeters. Just by looking at the graph. So again, if you have a graphing calculator, you should still be able to graph those. If you don't, use this. This works fine, seems to be. So any questions on this example? Are we good? All right. So let's take a little break and then we'll continue. So section 2.2 is dealing with what we call algebra of functions. So for those of you who've read that, how many am I talking to? How much sense does that make? Especially the domain part. I know it's easy to add two functions, but the domain part, what? Oh, well, that's tough. So section 2.2, algebra of functions. So let's say we have function f. So let f be a function with domain A, and let g be a function with domain B. So we can define 4 basic operations from function, just like you have on numbers. You can add, subtract, multiply, divide functions, 4 basic operations. Now with functions, there's also a 5th operation that we can do on functions called composition of functions, and we'll do that in section 2.3. But for now, you only have 4. Add, subtract, multiply, divide. So those are pretty straightforward. If you understand how to combine like terms, so then you can add functions, you can subtract functions. If you understand how to FOIL, you know how to multiply. If you understand how to find common denominators and things like that, you should be pretty okay with it. The tricky part will be the domain of those new functions. But first, we defined the sum function, f plus g of x, that's the notation. So it's the sum function of f and g, which really means f of x plus g of x. But the domain of this new function, A makes f happy, right? F is defined on the set A, so whatever's in A makes f function well, right? That's the idea. Now, at the same time, whatever's in B makes G happy. You agree with that? So you have A works with F, B works with G. Now I have a function that consists of both F and G. So I have to make both of them happy. So how do I make both functions happy? If A makes F happy, B makes G happy, I want to make both F and G happy. What do you mean by that? Yeah, but isn't like there's a possibility that A might contain a number that will make G upset, or B might contain a number that will make F upset. You agree with that? Yeah, I want to find the intersection. So, both F and G happy. So, and gives you the intersection. So, you want to find what they have in common. Does that make sense? So, you want to find what both sets share, because their intersection making both F and G happy at the same time. So, this will be true for all other types of functions we're going to talk about. You will always want to make both of those functions happy. So, if I give you the difference function, which is f of x minus g of x, you have same situation. You want to make both f and g happy. So we're talking about the intersection of both sets, A intersection B. And so forth. We can define a product of functions, just f times g of x, that equals to f of x times g of x. So that's also an intersection. You have to make both functions happy. And finally, we can define a quotient of functions. Now, the quotients are always a little tricky. So f over g of x, which is f of x over g of x. So again, we have to make f happy, we'll have to make g happy. So the intersection makes them happy. Right? As before, whatever both sets share, that makes both functions work well. But there is a little but here. Since we're adding a denominator, g is in the denominator now, what we need to avoid? Right, we need to avoid dividing by 0, so g shouldn't equal 0. So we need to do whatever is possible for g of x not to turn into 0. So we have to exclude the zeros of g function, right? Because we're putting a denominator, nothing prevents for g to just turn into 0, but it'll be a bad thing if it ends up in the denominator. So this is just the definitions, and again, the hardest part usually is finding the domain, and that's what you always want to do first. Just find that intersection of both domains, and that will be the answer almost to all questions. Okay? So I want to do an example. So example, f of x is x squared minus 4. G of x is x squared plus square root of x minus 1. So before we do anything else, I want us to find domain of f, I want us to find domain of g, and I want us to find the intersection of the both, because that will be the domain of all the future functions that we're building. So what is the domain of f? All real numbers. It's just a quadratic function, it's a polynomial, nothing to worry about. What is domain of G? Greater than or equal to 1, right. The way we do domains of the square root functions, again, we're going to take the radicand, set it to greater than or equal to 0, so x is greater than or equal to 1. X squared is fine, the square root might cause problems. So the domain here, we can just write it like this, from 1 to infinity. Is that okay? So what is the intersection? What do they have in common? One is just everything. The other one is everything from 1 and on. So where do they overlap? What? Right, from 1 to infinity. This is the overlap. Is that okay? All right. So that's the domain for the addition. That's the domain for subtraction. That's the domain for the product. The domain for the quotient will be different, but at least there will be a starting point. We'll start with that, and then we exclude all the numbers that turn denominator into 0. But now, if I ask you, find the following functions, and state the domain, we already answered domain question in 3 out of 4 cases. But the f plus g function literally means take f, add it to g. So there's not much going on. It's just x squared minus 4 plus x squared plus the square root of x minus 1. You're just adding f and g. Combine like terms, so it's 2x squared. That's a plus in there. So what is the domain of this function? Yeah, we already found it. So the domain is 1 and up, including 1. If I ask you to subtract these two functions, you have to be a little careful with subtraction. You have to make sure that you subtract the entire function. So it's x squared minus 4 minus, put the g function in parentheses. This is how you make sure that the entire function gets subtracted. A common mistake, if you don't put parentheses, then you end up subtracting x squared and not changing the sign of the second part. So that means you're not quite subtracting the whole function. You're subtracting part of it, and you're adding another part of it. Does that make sense? Because with parentheses, it'll make sure that all signs change. So the squares cancel. So negative 4 minus the square root of x minus 1. Domain stays the same. None of those computations affect the domain at this point. The product, same idea. So that's x squared minus 4 times x squared plus the square root of x minus 1. I don't feel like opening that up, but that's the idea, right? If you had to, you can FOIL. Domain doesn't change, still from 1 to infinity. Right? I don't need to even look at that function to know the domain anymore. So let's do this function, g over f. I want to put f in the denominator. So that's the square root part over x squared minus 4. Okay? So what's the domain of that function? Same without 2. What about negative 2? Do I have to worry about negative 2? Why not? Well, I mean, technically, negative 2 will turn the denominator into 0, right? But, I mean, you're right. I don't need to worry about negative 2. I just want to make sure we all understand why. In this particular case, we don't need to worry about negative 2. Hmm? Why? Right, because this is our starting point from 1 to infinity. So negative 2 is already excluded by default. So I don't need to even worry about this. The only number on that interval that still causes problems is positive 2. So that's the only one that I need to remove. Does that make sense? Because negative 2 is already excluded from 1 to infinity. So you're right. So you just need to exclude exclude positive 2 from there. Negative 2 is already out of the question. So then the domain here would be everything from 1 to 2 union from 2 to infinity. This is how you drop a number out of the interval. Okay? Or you can write it as a set, all x's, such that x is greater or equal to 1 and x does not equal to 2. That's also acceptable. The same thing. Does that make sense? Okay. But again, be careful, because, if we didn't have any of those square roots, it was everything but 2 and negative 2. Negative 2 would be a problem maker. All right. Let's try, let me mess with you now. So f of x is x plus 1 over x minus 2, and g of x is x over x plus 3. So to answer domain question is pretty straightforward, right? What is the domain of f? Everything but 2, because that's the only number that turns the denominator into 0. What is the domain of g? Everything but negative 3. That's the only number that turns the denominator into 0. So then the domain for the sum, difference, and product will be the intersection of these two sets. So if you find the intersection of A and B, what is the intersection? Is 2 going to be in the intersection? Is negative 3 going to be in the intersection? No, but everything else will be. So it's everything but 2 and negative 3. That's the intersection. Okay, putting everything together. So if I add them, subtract them, multiply them, that will be the domain of those functions. So let's do the difference. F minus g. Let's actually compute that one. So it's x plus 1 over x minus 2 minus x over x plus 3. So I'm subtracting two fractions. In order for me to do that successfully, I need to do the whole common denominator thingy. What is the LCD here? Right, I need both of those factors because they're very different. X minus 2x plus 3. So that means I need to multiply the first fraction by x plus 3. I need to multiply the second fraction by x minus 2 to bring them to the same denominator, just like with any other fractions. So overall, this whole thing will be x minus 2x plus 3 in the denominator. In the numerator, it's x plus 1 times the missing factor, which is x plus 3, minus x times x minus 2. See what I did? I'm kind of skipping a step in there, but you should be able to see that, right? You see what happens? Yeah. So FOIL, x squared plus 4x plus 3 minus x squared plus 2x. I FOILed and combined like terms. Sorry, I'm making those computations go faster because you're good at FOILing and all that stuff. So overall, that's 6x plus 3 over that. But what is the domain of that function? I mean, we already found, right? We don't need to do it again. It really gets strange when we start dividing this. Yeah. Well, you just change your denominator and the numerator, but the idea stays the same. Just make sure your denominator is not 0, right? But yeah, I can swap. I can go g minus f. That, you just replace your functions. But in this case, so we're dividing f and g, so it's x plus 1 over x minus 2 divided by x over x plus 3. Without doing any work, can you tell me the domain of that new function? You should be able to. Because remember, the domain of the quotient is still the intersection. So it's still going to be x cannot equal, what was that? 2, x cannot equal -3. And whatever makes denominator function, whatever makes g equal 0. So here's g. What makes g equal 0? What x value turns g into 0? 0, right? The only time a fraction can be 0 is when numerator is 0. So just x. So I have to exclude 0 from my domain. So you see, whatever I started with, and then think what makes your denominator function turn into 0. When I actually do the work, it's going to look, it'll look like this answer is wrong for the domain if I actually compute the quotient. But that's the right answer, because that's how we defined it. Is the intersection in addition to whatever makes the denominator function, which is g in this case, equals 0. Not just denominator, but denominator function. So if I do the work, how do you multiply? I mean, how do you divide fractions? Yeah, multiply by the reciprocal, and then you just multiply straight across whatever x plus 1, x plus 3 over x times x minus 2 is. Right? You just multiply. Is that okay? I'm not going to distribute anything like that. I like this answer. But look at this function. If I just wrote that function on the board without any of that other mumbo jumbo, and if I told you, here's a function, what's the domain of that function? You would say, well, everything but positive 2 and 0. There's no problem with -3 as it's written. Do you agree with that? If I just write this function in the circle here, -3 is perfectly okay. If I plug in -3, I'll get 0 for the answer, right? But since we build this function as a ratio of other two functions, -3 was a problem for one of the original functions. So this is why -3 is excluded from the domain. Okay. So again, we're just sticking to the original definition. It's just the intersection, remove the zeros of the denominator function. Does that make sense? So this is what I mean by that. This answer might actually appear wrong to what function looks like in the end. But through the definition, -3 was causing problem the way the function was set up. Okay. Let's flip them. Let's do g over f. So it's kind of answering your question. I mean, I can flip it. The idea stays the same. I'm just replacing it's x over x plus 3 divided by x plus 1 over x plus x minus 2. Again, without doing any work, I can answer the domain question. Because the domain, again, I'm starting with that intersection. Everything but 2, everything but negative 3. And then I have to make sure that my denominator function is not 0, which is f. Right? F is my denominator function, is this guy right here. So ask yourself, what makes that function equal 0? Negative 1, right? Whatever makes the numerator 0. So that's the thing I need to exclude. X cannot equal to negative 1. Because that will make that denominator, that big denominator function equal 0. Does that make sense? Now if we proceed, we'll have to flip it and we'll write it out. And it will feel like, again, that the answer does not correspond to what it should be, but that's the right answer. You start with the intersection, and then you look at what makes the denominator function equal 0. It's kind of weird, but hey, that's where we are. Because that's how we define things. Right? That's how math works. We gave it a definition, and we're sticking with it. Okay. So the next thing in this section, and especially for those of you who've read it, and some of you actually wrote it, that thing, it's called difference quotient. So good catch. That's important. Now, I'm not going to go into greater details of what the difference quotient does or what the difference quotient is. Some of you might have encountered in other math courses, but the idea of a difference quotient is very similar to finding the slope of a line, but a very special line. Let's say I have a function, nice pretty function f, and I have a point on that function. Let's call this point x, and let's call this point, well, f of x then. So the coordinates of these points are x and f of x. Okay? And I'm going to take a second point on that function a certain distance away from x. So let's call that distance h. So h units away from x, so then this point right here is x plus h. Right? X, h more, x plus h. And if I go up to the graph, then the height is f of x plus h. Right? Now all I want to do, I want to connect these two magic points with a line. This is called a secant line, the line that slashes through a graph, making two or more points with the graph of a function. And I want to find the slope of that secant line. Okay? Well, that's easy. How do we do slopes? Change in y over change in x, right? So what's the change in y? This point minus that point, right? So it's f of x plus h minus f of x. What is change in x? H, right? Because we actually put a value to the change in x. It's x plus h minus x. That's h. So this little expression is called difference quotient. Because there is a difference and there is a quotient. Difference quotient. Not very creative, but hey, that's what we call it. Right? So now our job is to evaluate difference quotients of different functions. And that's going to get a little fuzzy. We'll just have to remember one thing. Because, it feels like you can keep going with your math. Your goal is to kill that h. Just kind of maybe write it down somewhere. It's an unofficial goal, is to kill the original h in the denominator. You might get a bunch of new h's in that denominator, but you're after the original h. Okay? Some of you might have, somebody encountered that thing in my other courses. Um, the idea is to, the big picture, again, don't write any of that down, but the big picture eventually in the future math courses would be to find the slope of a, what we call a tangent line. The line that just touches the graph of a function at a point. Okay? Now, if you think about this, so you only know one point on a line. Can you find the slope of a line knowing one point? How? But how do you figure the rise if you only know one point on the line? So you need 2 points, right? Because you're right, it's rise over run. So, but it's rise between 2 points and it's a run between 2 points. But you only know 1 point now. So what we're doing, we're picking another point, kind of a certain distance away from the point that we know of, and then we're going to make this h very, 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 very small. So we're virtually having a secant line that's almost same as a tangent line. So this h will eventually going to become 0. So then it's a problem. You have a 0 in the denominator. So our job is to simplify it in a way so it's no longer a problem. But the story there, it's, you don't need to know that story. So let's just try to compute difference quotients of different functions. So here's a simple example, just to find different quotients. So let's say f of x equals negative 2x plus 1. So that's a function. I want to find the difference quotient of that function. Now you can actually guess the answer, and you're probably going to be correct if you understood how we derived the formula. Because the difference quotient is just the slope of a secant line, right? Now, if your function is a line to begin with, so if you connect any 2 points on the line with the line, what do you get? You get the same line back. So what is the slope of that line? Negative 2. So that's my prediction, that if I take this formula and I apply it to that function, the answer will come out to be negative 2, because that's what we're looking for the slope, just the slope. So this is how we set this up. There are 3 parts to this formula. First, we need to figure out what f of x plus h is. And I already asked you that question before. How do you do f of smiley face? And you're all laughing at me, but you understand the concept. Whatever's in the little parenthesis replaces the variable. So then f of x plus h becomes negative 2 times x plus h plus 1. Right? That's f of x plus h. Then the formula tells me, I don't know if you can see that, put a minus, so it's minus the original function. So I have to subtract the original function. So I have to put it in parentheses to make sure that all signs get distributed. Right? So this is minus f of x. And it's all over h. So here are the 3 parts. F of x plus h minus the original function, f of x, all over h. This is the hardest part, by the way, is to set it up. If you can set it up, if you can set this up properly, it's 50% of success. The rest is just opening up parentheses, combining like terms, and not violating rules of algebra. But check this out. Let's do that. So distribute negative 2. So it's negative 2x minus 2h plus 1, and then plus 2x minus 1 all over h. And again, we're after that original h. We want that h in the denominator to go away. So I can cross out a bunch of stuff in that numerator, right? What can I cross out? I can kill 2x. I can kill 1. We're down to negative 2h over h. So negative 2. And that's going to be true with every linear function because it's just going to overlap your line perfectly, so it will share the slope with your line. So that makes sense. Any questions on the setup? How we did that? Okay, because the rest you should be okay with. I'm just opening up parentheses. There's nothing fantastically interesting there. Just the setup. Setup okay? All right, let's try something more interesting. Let's do a nonlinear function. Let's say g of x is, well, 2x squared, I'm just making stuff up, minus 5x plus 3. So I want to do that one. A quadratic. So again, we're going to set it up with evaluating this function at x plus h. So x plus h goes in for every x in that function. So that becomes 2 times x plus h squared minus 5 times x plus h plus 3. So every x turned into x plus h. So this is g of x plus h. Is that okay? All right. Subtract the original function. So minus, put the original function in the parentheses. You will, otherwise you'll lose a sign. That's another bet I can make right now. It's $200 on the line. Not bad on that one? I'm telling you, just put, every time you're subtracting anything, just put a parenthesis. Worst case scenario, it's an extra set of parentheses. They'll just go away anyways. The parentheses, over parenthesizing is hardly ever a problem. Over h. So that's g of x. Again, you don't need to label it. I'm just showing that's a learning tool. You don't need to label it like that. But that's the idea. It's your function at x plus h minus your function as it's written originally divided by h. Okay? So now we have to open up all the parentheses, combine like terms, and hopefully that original little tiny h from the denominator will go away. That's what we want to kill. So, how do we square x plus h? What is that equal to? X plus h squared, what is that? Very good. X squared plus 2xh plus h squared. We went over that formula. Then distribute 5, negative 5, so it's minus 5x minus 5h plus 3. Then distribute the negative, so it's negative 2x squared plus 5x minus 3 all over h. I can already cross a few things out, right? What can I cross out? 5x. What else? 3's. And I'm almost ready to kill the x squared part, right? When I distribute the 2, it's going to be ready. So distribute the 2, it's 2x squared plus 4xh plus 2h squared minus 5h minus 2x squared all over h. Huh? So, yeah, 2x squared can cancel. Nothing else I can do with that, right? There's nothing else that I can combine or simplify. But there is at least one h in every term in the numerator, right? Whatever's left has at least one h. So I can factor h out from the numerator and cancel it with the one in the denominator. You see that? There's at least one h in every term in the numerator. So this is h times 4x plus 2h minus 5 all over h. So those two cancel. So 4x plus 2h minus 5. That's the answer. That is the value of difference quotients for that specific function.
You always be able to get the h to cancel.
Not always. I mean, I can make up functions that, but with polynomials, yes. I'm about to toss you a fraction, and the square root function will still be able to work with that. But, you know, it will get messy. But, yeah, theoretically, you should be able to. And there are some shortcuts you might learn in your future math courses. But questions on here, how we set it up and how we carry out the computations. Because, again, the importance of this, we interpret the slope in many different ways. And one of the interpretations of a slope was rate of change, average rate of change. Okay? So the slope between 2 points will be the average rate of change. So the slope of a secant line between 2 points on the curve will tell you, on average, how fast this function was growing or decaying on that interval. Now, if you make that secant line into a tangent line, you make that interval small, you're getting your instantaneous rate of change. So when you're getting a speeding ticket, that's the math behind your speeding ticket. They're trying to figure out how fast you were going at that moment. Right? It's never, on average, you were going this fast. You don't care. It's how fast you were going at that instant. Anybody ever got a speeding ticket for average speed of a trip? That happens sometimes. I'll tell you that story. I can get a speeding ticket. They'll tell you, oh, on average you were going 90 miles an hour, so you know that's a speeding ticket. Yep. Yeah, when you go on a toll road, they give you a little ticket, or you have one of them fancy, or now it's they just take pictures of your license plate apparently. They know the time they took the first picture, and they know the time they took the second picture, and they know the distance between the two cameras. They have 2 points, so they know the average speed between the two tolls. Sometimes they'll say, well, you know, you drove the 2 miles at average speed of 95 miles an hour. There is a theorem in mathematics that will tell you if your average speed is 95 miles an hour, there was at least one instant when you were going 95 miles an hour, and you'll get tickets for 95 miles an hour. Even though sometimes you might have gone faster, sometimes you might have gone slower, but your average speed, there's always a moment when you were going your average speed. So you cannot argue like, well, officer, although on average I was going 95 miles per hour, my speedometer never went above 60. And I'll say, well, no. Because of the theorem of mathematics, blah, 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 and they can do that. But yeah, so be careful. They used to do that in New Hampshire, but that's a totally different story. Because New Hampshire is, you know, when you go on the East Coast on 95, New Hampshire is about that big. And you can cross New Hampshire in like under 10 minutes. So you always kind of call your buddy, hey, I did New Hampshire in 6 minutes. And then, oh, there's a speeding ticket in the mail. Because they do that little, you know, here's the ticket, pay the toll on that exit. Anyways. So, but how's math? Does math make sense? Again, the hardest part is the setup. When you set it up, then it becomes a basic manipulation of terms. So, I have 2 more functions I want us to do for this. I don't know if we have time for 2. I think we do. Oh yeah, 7 minutes, plenty. Well, maybe. I'll go fast. 1 over x. So the setup, how do you do f of x plus h? What is it, f of x plus h, if it's just 1 over x? Where does plus h go, on the side or on the bottom? On the bottom. Because that's a reciprocal function, just flips everything. So it's 1 over x plus h minus the original function all over h. That's the thing, right? F of x plus h minus the original over h. The trick here, to simplify this fast, is to find the LCD for all little expressions. So the LCD here, I have a denominator x plus h. I need it. I have a denominator of x. I need that in my LCD. What's the denominator of just h? 1, so it doesn't contribute, right? So this is kind of the thing that maybe feel a little weird. H is in the denominator, but h itself does not have a denominator. Does that make sense? So that's the LCD. So what you want to do with that, the quickest way to simplify this expression is to multiply and divide by that LCD. Is that a legal move? Multiplying by 1, always legal, right? That's what I'm doing. I'm multiplying by 1. So now check this out. If I take this expression and I distribute it, so I have 1 over x plus h and just x plus h. So x plus h is going to cancel. Right? I'm multiplying by x plus h, and I'm dividing by x plus h. So the x plus h cancels. What's left? If I just do this first product, this expression multiplies the numerator. So x plus h will cancel. You're left with x minus the second product. What is going to cancel? And what's left? And x plus h, right? X cancel, x plus h left, still in the parentheses. Now over here, it is a straight up product. There's nothing fancy. So then it's just hx x plus h. There's nothing canceled, just multiply straight across. Right? That's how you multiply fractions and you distribute. So now the rest should be pretty straightforward. We distribute the x. So x minus x, they go away. You're down to negative h over hx x plus h. And so then h is canceled. And this was my original h. This little guy was the original h from the original setup. I got a new h in there, but I don't care. I killed the original one. Because again, this thing kicks in when h is very small, when h basically 0, and there's absolutely no problems with setting h equals 0. Doesn't cause anything bad. Is that okay? Good. Now I'm going to really go fast for this one. The square root function. This is going to be fun. So a function takes the square root of whatever. So if I want to do f of x plus h, it becomes square root of x plus h minus the square root of x all over h. Right? So that's f of x plus h minus the original function all over h. Now, in order for me to simplify this, I have to get rid of those square roots. There's no other way for me to do that. And now, again, remember, when you're dealing with fractions and you're trying to simplify fractions, the only legal move that you have is multiply a fraction by 1 or add 0. That's another legal move. Multiplying by 1 does not change the fraction. Adding 0 does not change the fraction. Okay? So, how do I kill all those square roots? Now, this is how we're thinking about this concept. It will be really nice if, for whatever reason, this happened. You agree with that? If that happened, then the square roots would go away, and we would be happy campers, right? Now, what I just did, is that legal? No. So I need to multiply this by something so those little 2's appear. Okay? Now, I remember this formula. Right? The difference of squares formula. You see how those little 2's appear on the right? So I can think of my problem as that I have a minus, right? I have an expression with a minus. Well, if I multiply with the expression with a plus, then the difference of squares formula kicks in. So I'm going to go ahead and multiply the numerator by the square root of x plus h plus the square root of x. And then I'll have to multiply the denominator. So I'm multiplying by 1. My 1 is extremely creative, but it's still 1. And then I have the difference of squares formula in the numerator. You've done this before when you were rationalizing the denominators of things like that. This is kind of rationalizing the numerators. Same idea. So difference of squares formula kicks in, so that leaves you with square root of x plus h squared minus square root of x squared over big mess in the denominator. So the little squares kill the square roots. Numerator becomes x plus h minus x all over h and all that nonsense. And then you see that we just killed that h, right? X minus x go away. And we're down to h over h times the square root of x plus h plus the square root of x. And then h is canceled. So then it's just 1 over the square root of x plus h plus the square root of h. That's another case where I got a new h in the denominator, but if I set that one to 0, it does not cause any problems. And we won't be doing that. We won't be setting any zeros to anything. Our goal to kill the original h, and we've achieved that goal. If all my stories about speeding tickets didn't make sense, that's fine. You don't need to know what that thing is all about. That's just, set it up, simplify it, kill the h, and you're good. Is that okay? All right. See you next week. Is that what's going on?